Welcome to our team siteBeacons for Digital Tribes Unearth. Our team is composed of Ben Coman, Information Technology degree with Masters in Electrical Power Engineering, Caroline Coleman with the Marketing, Media Sales, Commercial Law degree with a background in Procurement and IoT Enthusiast, Nancy Chen Zong, final year student at UWA Electrical and Electronic Engineering, and Samuel Chang, a peon that says work.
So here's our user stories. The first scenario we considered is about surface mining equipment, SME, interacting with light vehicles and personnel. The second one we considered is about safety cones transmitting a circular region which interacts with light vehicles, SME, and personnel. We also considered personnel working from heights and the active mining area.
Here we have our site beacon designed for easy attachment to existing safety cones. On top we have a solar panel to extend the length of time between servicing to reduce maintenance costs. Inside we have the same internals as every one of our other site beacons, the GPS module, the ESP32 Bluetooth transmitter, and here we have a larger battery than we normally have on the personal units.
So this is the snip band for personnel equipment.
And here we have our site beacon for the vehicle, held on by neodymium magnets.
So our choice of technology was based on our understanding from the mentors that safety cones are put out in the field at hazardous areas, and they need to last 72 hours was the minimum, but a longer period would reduce labour for maintenance. So this triangle shows 3G has a lot of power usage, even though it has good range. In the mid we have the Wi-Fi, still a lot of power usage, and right down the bottom we have the RFID, but didn't provide the functionality required. So the next up from there was the Bluetooth low energy. To have quick response, rather than have any authentication or handshaking from a connection-oriented protocol, we've gone for a connectionless protocol that's advertising just out from the beacon. The receiver, what gets advertised out is the GPS coordinates of the device and also the exclusion zone configured in the device. For vehicles, that zone adjusts with its velocity. It gets longer in front of the vehicle, and that's transmitted to the receiver. The receiver can then determine whether they are in a safety exclusion zone. So our choice, we were given the Raspberry Pis, but the Raspberry Pis were still considered too much of a power draw. So we've gone with the ESP32. It provides Bluetooth and also a Wi-Fi connection for management, but the normal operation would be with the Bluetooth. And our GPS module, the VK2828, provides NEMA GPS information over a UART to the ESP32, and that transmits it via Bluetooth to another ESP32, which calculates the distance. So here we have our vehicle in motion, and the azimuth is the direction that it's travelling, and the vehicle, depending on every vehicle will have, depending on its size, its braking capability, and how it's loaded, will change the size of the safety zone in front of it. So it calculates its own 4 corners, which are the red dots, the safety corners. it calculates those 4 dots and transmits that information to the receiver, who can then determine whether they're in the zone and alert the personnel. Here we have the management unit. We considered Java and Android, but there were too many versions of Android, and we also wanted it to run on the iPhone. So the technology we chose was HTML JavaScript in a web browser that can run on PCs, Android and iPhone. It also allowed rapid prototyping as we were in development. And here we have the prototype in operation. The distance is displayed on the screen. In the far distance is a second transmitter, and as we move towards the transmitter, GPS calculates the distance between them.